Okay, so we left off last class using the notes on driving statistics, and we went over distance equals rate times time. We looked at the function here, put it in Desmos, and found that the optimum miles per hour was 49 miles per hour for the best gas mileage that you can get in a car. We also looked at several different cars and their tank size and the miles per gallon to figure out how many miles you would get on a particular tank. That is something to consider when looking for a car is, how many miles can you get on a tank of gas. If you do a lot of driving, it can make a difference on how often you stop to get gas. So, and that's where we finished. You were asked to do these 4 examples here. There's 2 on this page and then 2 on the next page, using the very simple form of distance equals rate times time. So let's look at the formula again. The formula is distance equals rate times time. And rate is just speed, however fast you're doing something. So in the first problem here, it says a car travels an average rate of speed of 50 miles per hour for 6 hours. How far does the car travel? Well, you just plug in the information that you have. 50 miles per hour is a rate, and 6 hours is time. So if you plug it in the formula, D equals rate times time, and you'll get a distance of 300 miles. And that's the answer there. Very simple, just using the application of distance equals rate times time. Now the second question says Jack lives in New York and he's going to be attending college in Atlanta, Georgia. The distance between the 2 cities is 883 miles. Now Jack knows that the speed limit will vary his entire trip, but he's going to travel at an average speed of 60 miles per hour. So approximately how long will it take him to get there? Again, the same variation, it's just a different variation of the same function. All you're going to do is plug in the values that you know. Well, in this case, it gives us the distance of 883 miles. 883 equals, but it doesn't give us the rate. It gives us the rate. It doesn't give us the time. It gives us the rate of 60 miles per hour times time. We don't know how long it is. That's what it asks us for. So we're going to solve this equation simply by moving the 60 over and dividing both sides by, that's supposed to be 60. Divide by 60. And that will leave us with time equals 883 divided by 60. Let's see here. Let me get a calculator ready. 883 divided by 60 equals 14.72. So that's 14.72 hours. And that would be the answer to that question. Now on to the next page. So on example 3, it says Kate left Albany, New York, and traveled to Montreal, Quebec. The distance between the cities is 216 miles. If it took Kate 3.5 hours to get to Montreal, what was Kate's average speed? Again, another variation of the same function, D equals R times T, where it gives us the distance of 216 miles, but in this time, instead of giving us the rate, it actually gives us the time. So we have rate times 3.5 hours. And just like we did in the previous problem, to get the 3.5 over to the other side, we're going to divide by 3.5, divide by 3.5, and that'll give us a rate. Let's see here, my calculator, 216 divided by 3.5, and that is an average rate of 61.7 miles per hour average speed. So that's all you do, really. This last question deals with miles per gallon. We already did this when you selected vehicles when we were doing the notes. Basically, if you go 40 miles, if you get an average of 40 miles per gallon and it's a 12-gallon tank, how far can you drive? At 40 miles per gallon, that is a rate for 12 gallons. That is, you just multiply the two, so 40 times 12, and that is 480 miles. That means on this particular car, on a car that gets 40 miles per gallon, on a 12-gallon tank, you're going to be able to get 480 miles on a tank of gas. Okay, so that's finishing up sort of what we did last class. Now, today's lesson is going to not be sort of on the distance equals rate times time, but now we're going to be looking at actual stopping distance. So we're going to be looking at reaction time and brake time. So you're driving down the road and something jumps in front of you, or maybe the car in front of you slams on its brakes, or a car accident happens in front of you, or for whatever reason you need to slam on your brakes. How long is it actually going to take you to stop, or how far are you actually going to go? We talked about in class the reaction time being 1 second. The average reaction time for a person is 1 second, and then after that, depending on your speed, how far are you actually going to travel before your car actually comes to a complete stop. So stopping distance is not just once you slam on the brake, how far are you going to go, but it also takes into account the reaction time involved, which actually is a long distance that you travel in just a fraction of a second. So now the problem is that you're driving in miles. You're driving miles per hour. When you slam on your brake, you're talking about fractions of a second. So it makes no sense to use miles per hour when you're talking about how far are you going to go in a matter of seconds. So what we have to do is convert miles per hour to feet per second. If we can get it converted to feet per second, then we have something a little more realistic that we can use. Since we are using fractions of a second, we can tell how many feet you're going to travel in their stopping distance. So in order to convert miles per hour to feet per second, you have to know a couple conversion rates. Now, you're going to be given these on any sort of test or quiz, but basically 1 mile is 5,280 feet, and 1 hour is 3,600 seconds. So how we convert our speed into feet per second is illustrated down here. So let's take, for example, you're going 68 miles per hour. At 68 miles per hour, that's 68 miles in 1 hour. So you write it as a fraction, 68 miles in 1 hour. And then you're going to multiply it by the conversion. Since miles, 1 mile is 5,280 feet, and 1 hour is 3,600 seconds, you're just going to multiply straight across. And when you multiply 68 miles times 5,280 and 1 hour times 3,600 seconds and divide them, you end up with a ratio of 99.7 feet per second. Now that's driving 68 miles per hour. Obviously, you're going to be going different speeds, with different miles per hour. But basically what this means is that if you're driving at 68 miles per hour, imagine you get on Interstate 69 there in Fishers. The speed limit is 65 miles per hour. So it's not uncommon to be driving 68 miles per hour around Noblesville. So 68 miles per hour, you are actually traveling at 100 feet per second. 100 feet every single second. Okay, so now there's been a lot of studies done to do reaction time, and we talked about this, the average reaction time is about 1 second. So what that means, since you go travel at 99.7 feet per second, going 68 miles per hour, that means that before you even apply the brake, you've gone just about 100 feet. So let's look at this conversion here. So here's an example of when you would use that conversion. So what is the reaction speed for a car traveling 48 miles per hour? Well, the reaction speed is only 1 second. So we're going to find how many feet we go in 1 second. Since we're doing 48 miles per hour, again, we write it as a fraction, 48 miles per hour per 1 hour. And then we multiply by the conversion, which is 5,280 over 3,600. And when you do that, when you multiply fractions, you just simply multiply straight across. So 48 times 5,280 is 253,440. And then 1 times 3,600 is just 3,600. And then all you do is just divide the two. So then I'll divide by 3,600, and you get 70.4 feet per second. So what that means is traveling at 48 miles per hour, you'll go 70.4 feet per second. Now, since we only wanted the reaction distance here, and that's 1 second, that means that going 48 miles per hour, you're going to go 70 feet before you even apply the brake. So that's that. And then it says, what about 25 miles per hour? So you can make the same conversion for 25 miles per hour. You do the exact same thing, except you do 25 times 5,280 and then divide it by 3,600. And even going 25 miles per hour, and that's driving through a neighborhood. And you're driving through a neighborhood anywhere here in Noblesville, going 25 miles per hour, you're going to go 36.7 feet per second. That's going a pretty good distance in just 1 second, especially if somebody or a kid goes out for a ball in the middle of the street and jumps out in front of you and doesn't see you. That could be a difference of hitting a kid or not. So that's reaction distance. Now, braking distance is a little bit more complicated. That's just the reaction. So we know that we have 1 second of reaction time. So both of these times, these distances, are just the reaction part. After you've reacted and you've applied your foot on the brake, now you're going to go what is called the braking distance. Now, this varies a lot. I mean, it depends on a lot. It depends on road conditions. Is the road wet? Or is there snow? Or is there ice? Is it asphalt? Is it cement? Is it brick? What are you actually driving on? That makes a big difference. But scientists have boiled it down to a pretty simple equation, and this is just an average. It is not exact models here, because you would have to take into account the condition of the road, the condition of your tires, how much your car weighs, even. A lot of factors go into how far it takes you to stop, but this is just an average. So all you do is take your speed and square it and then divide by 20, and that is how far you will go after applying your foot on the brake. And this is assuming that you're slamming on the brake. Okay, your wheels lock, everything, and you slam on the brake. None of this gradual stopping thing. So let's go to the next page and do a couple examples here. So it says, using example 1, find the braking distance for the same speeds. Well, the first speed was 48 miles per hour. So 48 miles per hour, all we do is simply square it and divide by 20. So then that'll tell us the braking distance. Well, 48 times 48 and then divide by 20 is 115.2. So traveling at 48 miles per hour, if you slam on the brakes, you're going to travel an additional 115.2 feet. For 25 miles per hour, okay, we take 25 and square it and divide by 20. So 25 times 25 equals, and then divided by 20. So even at 25 miles per hour, you're going to travel 31 feet approximately after slamming on the brakes. So to get the total stopping distance, what do we call the total stopping distance? We have to add the reaction time as well as the distance it takes to actually apply the brake. So what you would do is you would add this to the reaction distance, or what we call RD. Add the reaction distance to get what we call the total distance. Okay. Total distance is your reaction time plus the braking time. And that's the total distance you're going to travel. So let's look at that. Example 3. Rachel's driving at 48 miles per hour. So she's driving at the speed above. She sees an accident directly ahead of her about 200 feet away. Is she going to be able to stop in time? And we can figure this out. So she's traveling at 48 miles per hour. First of all, we need to figure out the reaction time. So 48 miles per hour, how we figure out the reaction time, 48 miles per 1 hour, we have to convert it to feet per second, which is 5,280 over 3,600. So what that is, do 48, and I know we already did this, but it's on a different page. So 48 times 5,280 and divide by 3,600. And so this is the reaction, 70.4. That's just the reaction distance, so we call RD. And then the stopping distance is when you take the miles per hour, square it, and divide by 20. So 48 times 48 and divide by 20 is that 115. Let's see if I can write 115.2. So that is now the stopping distance, we'll call SD. Now, the total distance is your reaction time plus the stopping time. So if we add those, we get a total of 185.6 feet is the total stopping distance. That is the reaction time and your brakes applied to the car. So if the accident, it really is 200 feet away, she sees it, slams on the brake, she will have enough distance to cover in front of her without hitting anybody. Now, this is important. This is why we don't tailgate. Look at this. I mean, they're only driving 48 miles per hour. Most streets in Noblesville, most roads you're driving on in Noblesville that are not in a neighborhood, you're going to be driving over 45 miles per hour. Okay, so if you're driving over 45 miles per hour, that is why we don't tailgate. Don't tailgate. Okay, at 48 miles per hour, by the time you react and slam on the brake, you're going to travel 185 feet before. So it's important. I mean, tailgating, I mean, there's people at tailgate that are, 15, 20 feet behind. There's no chance. They would have no chance. If the person in front of you slammed on the brakes, you would have no chance of avoiding that accident. And so that's a lot. I mean, that's over half of a football field you travel just going 48 miles per hour and then slamming on your brakes. That is it. That's the end of the notes. You have practice questions. I believe there's like 5 or 6 practice questions. There are answers at the bottom of each page. So your assignment is to go through and do the practice questions. You'll have an outcome quiz next class. It's the last outcome quiz. the last outcome quiz prior to your unit test and prior to your final exam. The next class is your last outcome quiz of the semester, and it's going to cover this material. So make sure you go through this and make sure you know how to answer all the questions. If you need any help, you can come in during AL on Monday or send me a message on Canvas. Thanks.